Designing for concurrency. In a previous nugget, designing lock granularity, we were way down in the details of how SQL Server issues locks, the different kinds of locks, how we manage locks, and how we deal with blocking and deadlocking. Concurrency related stuff. This nugget's going to take a step back and look at the overall concurrency picture. What is concurrency? What is a transaction? What is optimistic versus pessimistic concurrency? And getting familiar with isolation levels, because understanding isolation levels will help us develop the right concurrency strategy for our application. And Microsoft had a really good quote that I like when it comes to concurrency. They said, every user should feel like they're the only user in the system. Because if our users are constantly waiting on each other or other processes to finish, then we know we have an issue with concurrency. So this nugget's all about understanding how to design for concurrency and also understanding our isolation levels so we can find the right level of concurrency for our application. So we'll kick things off here with the basics. What is concurrency? What is a transaction? What is the difference between optimistic and pessimistic concurrency? We'll also talk about the side effects of concurrency. There are a few, because anytime you have multiple people or processes accessing a shared resource, whether that be a Word document or data in a database, things can happen. What happens if two people update that resource at the same time? What happens if someone tries to read one that's currently being updated? So we'll check out what lost updates are all about. We'll talk about dirty reads, non-repeatable reads, and phantom reads. And we'll also talk about isolation levels. Get familiar with all the different isolation levels, which will help us deal with those problems amongst others. Then we'll jump into the virtual nugget lab. We'll get a concurrency demo. I'll give you a good example of each one of those concurrency side effects that you'll see out there, and also give you an example then of each isolation level and see how they work. Armed with all this knowledge, we should be able to come up with a good concurrency strategy for all different areas of our database. Let's start with the basics. Concurrency can be defined as multiple processes accessing, whether that's reading or writing, shared data simultaneously. High concurrency is defined when you have many users accessing a resource simultaneously and they do not interfere with each other. On the other hand, low concurrency is when you have multiple users accessing a shared resource and they're all queued up and waiting on each other. Now, there are two concurrency models out there. One is the pessimistic concurrency model. This is the default in SQL Server. Pessimistic means it's going to issue locks on resources to protect them. So we're going to get lower concurrency but higher data integrity. So it avoids conflicts by locking, and it can also block other processes, but essentially readers block writers, writers block readers and writers. That is really the essence of pessimistic concurrency. Optimistic concurrency does not use locks. It uses row versioning and timestamps, and essentially what happens is if two people were to modify the same record at the same time, optimistic concurrency would take a snapshot of that old record, store it somewhere, and then if anybody were to read data while those updates were going on, it can reference the old record. So it uses row versioning to allow readers to see the state of the data before the modification occurs. So with this model, readers do not block writers and writers do not block readers. Writers do, however, block writers. So what this comes down to is pessimistic locking is most often used when you expect a lot of collisions. That being many processes or people accessing the same resource at the same time. That's also why it's the default here in SQL Server. We may have lower concurrency, but again, we have higher data integrity and protection. Optimistic concurrency is used when you do not expect a lot of collisions. So you get better concurrency, but you'll pay a bigger price when a collision does occur because you're going to be the one responsible for conflict resolution or designing conflict resolution in the database. Moving on to transactions. What is a transaction? It is a basic unit of work in SQL Server. Everything you do is wrapped inside of a transaction, whether you do it on purpose, explicitly, or you just submit one statement, one update statement, or one insert statement. It is a transaction. And we'll get into the differences between explicit and implicit transactions in a future nugget. But for now, just know that everything in SQL Server is a transaction. A transaction is just simply a sequence of steps that will result in either success or failure. In SQL terms, that means commit or roll back. It's either going to get saved or it's going to get canceled. All transactions exhibit the four big properties, the four acid properties as we call it. Atomicity, consistency, isolation, and durability. Atomicity just simply means that our transactions are all or nothing. Essentially this right here, success or failure. Consistency just guarantees that a transaction can never leave our database in a partial state. Isolation guarantees that transactions are protected from one another. And this is the big property that we're going to be working with when it comes to concurrency, because we can control how transactions work with one another or affect one another. And then durability just ensures that pending changes can still be applied if a system failure were to occur. So transactions are durable in that sense that if they commit their work, no matter what happens, when that system comes back online, that data will still get pushed into the database. Now, to really understand how transactions work, it helps to visualize a process. And so let's say that we were on the internet, on Amazon's website, we wanted to buy a product. Now, I've oversimplified this for the example because I'm sure ordering a product off Amazon is way more complex than this. But let's just say, for example here, that we ordered a product, we clicked the buy button, Amazon would check the inventory. If it was good, it would create the order. If that was good, then it would update the inventory with the new value. So this would all get wrapped inside of a transaction, meaning all of these steps have to succeed for the order to actually get created and everything to go through. If any of these steps failed, it would get rolled back and it would be like it never happened in the system. That's the essence of a transaction. And in the back-end world, it would look like this: a select to get the inventory, an insert to create the order, and an update on the inventory. So again, in the back end, all of those things would have to succeed in order for the order to actually get created. Another popular example is the old ATM example where you're transferring money from one account to another account. It's a debit from one account and a credit in the other account. Both of those have to work for the whole transaction to roll through. Otherwise, you could lose money or gain money depending on which side failed. So that's a transaction and how they work. Now, the tricky part comes in when we start introducing concurrency into this, because say we have thousands of users, like Amazon, who has probably millions of users. Now, how do we handle all of these people accessing the same product, reading inventory, updating inventory? How does all that work? Let's go check out what some of those problems are and how we can control them using isolation levels. Let's start with some concurrency effects and lost updates. So lost updates occur when two or more transactions grab the same row, they read the same row, and then they update that row based on the value they originally selected. So each transaction is unaware of the other transaction's changes, and the last update will eventually overwrite the first update. That will result in the first update getting lost. Let me give you a real-world example of that one. So let's say that you and your significant other have a joint bank account, and there's $10,000 in that bank account. Today's Friday, you both got paid. Significant other number one, say they got a $1,000 check. Significant other number two got a $2,000 check. Now, here's the part that causes the problem. Is let's say that they're both at a different bank across town. They read the value of their bank account and store it locally here. So 10K, 10K. Now, the update goes through, and they're going to use that locally read value to update their bank account. So if significant other number one does a read, it's 10 plus 1 is 11, so they update their bank account to 11. Now, at the same time, across town, significant other number 2 does the same thing, and it updates it to 12. What happened? We lost significant other number 1's update because it went in first. But again, the big problem here is that this data was read first, and then it used that locally read data to update it. And this is something that SQL generally protects against, and the only way that this is really going to happen is if you have a developer that did it in their code. And it can happen by somebody doing something like this, pulling the data, storing it locally, and then using that data to update the existing database because they're using outdated data locally. So generally this can be avoided just by using an update statement rather than pulling the data, storing it, and then updating. But that is what a lost update is all about. The next three are going to be the big ones. So a dirty read happens when user A updates a record. So let's say user A updated this record. User B comes along and reads that record. They read that record, and then after they read that record, user A's transaction is rolled back. It's known as a dirty read because they read uncommitted data. The next three are going to be the big ones. So dirty reads. A dirty read is when a user reads uncommitted data from the database. An example here, let's say user A updates row number 1. All right, so they're updating a value here inside of row number 1. At that same time, user B comes in and reads that record. After they issue their select statement, they read the record, user A says, you know what, I'm going to cancel that. Or maybe a system failure happened. Whatever the rate, this gets rolled back. So that actually never really happened. But user B already read the data, so they're reading dirty data, uncommitted, invalid data. The second one here, a non-repeatable read, happens when user A reads a record and then goes and does something, and this is all still in the context of a transaction, and then user B does something to that data. Then user A's other statement comes in and reads that, and they get a different result. So within a single transaction, they read the same row twice and got different results. That's known as a non-repeatable read, hence the name. They didn't see the same values the second time that they read that same row within a transaction. And that's also known as inconsistent analysis. A phantom read is much like a non-repeatable read, but rather than at the value level, it's at the row level, and it applies to inserts and deletes. So let's say that user A once again had a transaction. The first transaction read rows 1 through 3 here. Then user B comes along and deletes row number 2. Now the second read isn't going to show row number 2 for user A here. So what that means is the first read, they read a row that doesn't actually exist, hence the term phantom read. So these effects, along with isolation levels, will help us come up with what's acceptable and what's not, and what kind of concurrency are we aiming for within our applications. So an isolation level is something that we can apply at either the statement level through table hints or the connection level, and they allow us to control what's acceptable when it comes to these potential side effects against our data. Starting with read uncommitted. Read uncommitted brings with it high concurrency, because we're not issuing any sort of read locks, at the cost of potential data inconsistencies. So read uncommitted is generally going to be good for reporting. Those big honking reporting queries that take forever to run, a lot of people do a with no lock. With no lock is essentially read uncommitted. It's the table hint for turning a query into read uncommitted so it doesn't issue any read locks. So it's good to use for reporting and aggregations and stuff, and when data inconsistency is okay. Read committed is the SQL Server default. This is a good balance between concurrency and consistency. It issues locks, there's a potential for blocks, but it is the default and the most common level. We avoid dirty reads, we do have the potential for lost updates, non-repeatable reads, and phantom reads. A repeatable read is a lot like read committed, just with the added protection of no non-repeatable reads. So it gives us higher consistency, again, locking and blocking just at a higher level than locking and blocking of read committed, because it can lock greater hierarchies. And you really don't see it used very often out there in the field. Serializable gives us the highest level of data protection and data consistency with the lowest level of concurrency, because we are protected from absolutely every one of these data issues. And you'll often see that used when you need high consistency, such as banking scenarios and dealing with currency and financial values. So these 4 that we just looked at are all ANSI SQL standards. These snapshot isolation levels are SQL Server specific. These last 2 are also in the optimistic concurrency category, because rather than use locks, they actually use tempdb to store snapshots of the data. So that way, whenever they change data, SQL Server takes a snapshot of that record, stores it in tempdb, and any other connections that come in that ask for that data will get that data stored in tempdb. So that's kind of nice for concurrency. It's a great way to increase concurrency. The only downside with snapshot is that it can be resource intensive, because SQL Server has a lot of extra work to do to keep track of all of these rows and the changes on them, and then serve those rows up to anybody requesting them. And the difference between these two, think of snapshot isolation much like serializable. We get all the benefits of serializable without having our data locked. So blocking and deadlocking will not be an issue. And then snapshot read committed, also known as RCSI, read committed snapshot isolation, is a lot like read committed without all the locking and blocking going on. So we can still get non-repeatable reads, phantom reads, and lost updates, but we're safe there from dirty reads, much like the difference between committed and read uncommitted. All right, why don't we head into the virtual Nugget Lab? We'll first get an example of each one of these concurrency effects, and then we'll get an example of how to use each one of these isolation levels so you can see them all in action. Here we are in the virtual Nugget Lab. Let's bring up SQL Server Management Studio. We have a new project inside of our solution, 15.concurrency. And what we're going to do here is we're going to need a couple of connections. The first thing we're going to do is just demonstrate these effects: lost updates, dirty reads, non-repeatable reads, and phantom reads. So let's get some screen space going here. And for the first one here, for lost updates, remember this happens because we read data and then we use that data to update the database. So this is what we're going to do. Session 1 here, we're going to call this Session 1, we're going to call this Session 2. In Session 1, we're going to begin a transaction. We're going to query the trainer table and pull the certifications for trainer ID number 1, which is myself, store it inside this variable. Then we're going to wait for 5 seconds. During that 5 seconds, we're going to flip over and issue an update, which is going to change that value to certifiable stud. And then we're going to come back and re-update that data based on the variable that we stored before that other update occurred. So this is going to essentially result in no data changes. This update is going to get lost. So we should not see the term certifiable stud for my certifications. All right, so let's do it. Let's go ahead and execute this. Within 5 seconds, then we need to execute this. I think I did. All right. See this? So over in this connection, it says, cool, my update went through. I'm a certifiable stud. But if we head back over here and we look at it, we updated it, then we ran the select, and it went back. So what does the state of the database look right now? Well, it looks like this one right here, my original certification. So what that means is this update, it's gone. It was lost. It never actually went through, or it was only there for a very brief amount of time. So how can we prevent this one? Well, we can prevent it by changing our transaction isolation level to serializable. This is going to ensure that these finish. This transaction needs to complete before this transaction can even start. So in this case, we should get the update that I am, in fact, a certifiable stud. Why, thank you. Thank you. All right, let's try it out. Let's go ahead and set the transaction isolation level. Let's run this, and then within 5 seconds, let's jump over and run this one. And what should happen is this one should be blocked. See that? We're blocked. We're blocked. And look at that. I'm a stud. And if we go back here and we run this one now, look at that. Cool. So that's how you can prevent lost updates, and that's a good example of what lost updates are. Serializable, along with anything that will create a lock or a block, they're not just serializable, will prevent lost updates from happening. The next thing we're going to show here is what a dirty read looks like. So remember, a dirty read is one that can read uncommitted data. So what we're going to do is we're going to start a transaction. We're going to update my trainer record, first name Darth, last name Vader, because with my name you were the brunt of many Darth Vader jokes growing up. Then we're going to wait 5 seconds, and then we're going to roll back that transaction. Now, before this transaction gets rolled back, we're going to switch over to session 2. We're going to change our isolation level to read uncommitted, because that is the only way we'll be able to read dirty data. And then we will issue a select statement against my trainer record. So this select statement should bring back that dirty data. All right, so let's do it. Let's run this. Actually, let's run it all just to show you that the select statement after the rollback will bring back my original data. All right, so we'll hit execute. We'll flip over. We'll switch the transaction isolation level, and look at that. It read dirty data. There it is. Darth Vader. What's the real data? Back to normal. And if we head back to session 2 and just resubmit this query, we'll see that we're back to the original data since it was rolled back. So that's a dirty read, and again, that's done because we set the isolation level to read uncommitted. Let's move on to non-repeatable reads. So with this one, remember, a non-repeatable read is one where we're going to read the same data twice in the same transaction and get different results each time. So to show this one, we're going to switch our isolation level to read committed so we can actually see the repeatable read, the non-repeatable read, I should say. And then we're going to issue this. It's going to read the data, and then within that 5 seconds, we're going to flip over to session 2 here, where we're going to submit an update. We're going to update the category Cisco to Crisco, because why not? All right, so let's do this. Let's highlight everything here. Switch it to read committed. In that 5 seconds, we're going to flip over, execute this. So that should update the data, and if we flip back here, we should see Cisco in our first one, and if we scroll down, Crisco in our second one. So that's what a non-repeatable read is, because our read didn't repeat. It was changed between reads within the same transaction. And now we can fix that by doing a repeatable read rather than a read committed. So this will prevent that. In fact, here, let's go into Nugget Demo DB real quick, and we'll just update our category the easy way here. Let's just change Crisco back to Cisco. All right. So this time we're going to do the exact same thing, just with repeatable read, which will prevent non-repeatable reads. So let's do the same thing here. execute, switch over here, execute, and now it's blocked. See that? It's blocked, it's waiting, and now we should get Cisco here, and we should get Cisco down here as well because it was blocked. But the real value, because after that our second one ran, and the real value here should be that it's Crisco. There it is. So we ensured that didn't happen there because we forced repeatable read, which ensured that we did not get a non-repeatable read. The last one we're going to look at here is a phantom read. And for a phantom read, it's a lot like a non-repeatable read, but rather than at the individual value level, we're at the record level. So we're going to pull back a bunch of records, then make changes to that records, and within the same transaction, we will query it again, and we should get different rows across both of these exact same queries. So just to show you here, it should look like this: Agile, Citrix, Cloud, CompTIA. We'll flip over to our session 2, add a record, which will get stuffed in the middle of that list, and we'll get different results on the second query. All right, so let's do it. Let's execute it. Flip over to 2 here, add a record, and now if we head back, when this is done, we should get a different set here for our second query, and we do. So Agile, Citrix, Cloud, Comp, Agile, ARG, Citrix, Cloud. So that is a phantom read. And the only way to prevent a phantom read is serializable on the pessimistic side and snapshot on the optimistic side. All right, let's work with isolation levels. Let's bring back Solution Explorer here for a moment. Let's open up isolation and isolation 2. So the first thing I just want to do here is show you how to view your current isolation level. And we can do that by a couple of ways. Number one, we could do DBCC user options. This will run us and give us the very last one here. You can see read committed, which is the default. And then another one here is using sys.dm exec sessions. There is a field in there called transaction isolation level. The result will be 0 through 5, and here are the isolation levels associated with them. And we're just going to grab that for our current session, and there it is. So read committed, that is the default. Now we're going to go through each one of these isolation levels, read committed all the way up to snapshot, just to show you how they work. A lot of this stuff we just saw in the previous demo, but we'll just do this by creating our own table and doing it straight up, so it'll make it really easy to see. So we'll create a table called isolation test that has an ID and just a varchar column here called some data. Then we'll put test through test 5 inside of this table. All right, so very simple table with a simple amount of data in it. And now the next thing we're going to do here is start with read uncommitted. And we've already seen this one. This is for dirty data. So it's pretty much the same thing, creating a transaction, updating that, waiting 5 seconds. In that 5 seconds, we can head over here, switch our isolation level to read uncommitted, and then read that data, and that should get us dirty data. All right, so let's do it. Let's highlight this, switch over to 2, execute it, and there is dirty data. Even though after that 5 seconds, we're going to roll back, and that data should be back because we rolled back. So we saw that one. I think you get the gist of how dirty data works. Let's move on to the next one here, read committed. Oh, and I did mention this. I just wanted to point out that I did put it in here as well, that it's the same thing as doing a with no lock. So you can use table hints to do this as well if you want to do it at the statement level rather than at the connection level. Because running what we're doing here, running our set transaction isolation level, we're switching the isolation level for the entire connection rather than doing it at the statement level. Back to read committed. So again, this is the default, and essentially what this is going to do is create a lock, and we're going to be blocked from reading while the update is occurring. So here we're going to run an update to update our second record, ID equals to changed, wait for 5 seconds, and roll it back. So what we should see over in connection 2 then is nothing. We shouldn't see any change at all because it'll get rolled back, and this query right here will block our second session. So let's run this, flip over to 2, and then run this, and see how we're blocked? We are blocked. And then when it finally does get around to running it, it's just going to return the same data. We do not see that changed value here because we rolled it back. So that's read committed. That is the default, and that will prevent reading dirty data. Now, repeatable reads. Remember, repeatable read just protects us from multiple queries within the same transaction, ensuring that they return the same value. So what we're going to do here is just issue a select against our isolation test, flip over to session 2, and then from here we will issue an update against that. And what we should see here is not differences between both of these queries. They should both return the same results. Again, we did see this one as well, but just to reinforce it here, we will see that this will be blocked until both of these statements complete. And they did. We have no changed value in any of them. And if we head over here, we should now have a changed value if we do a select. There it is. Number 3 is changed, even though session 1, because we had repeatable read on, didn't get those changes. Now, serializable, we're going to run the same test, but the big difference between serializable and repeatable read is that repeatable read does not protect against phantom data. Serializable does protect against phantom data. So let's do that same thing. Hit execute, switch over to 2 here, and run our serializable test here. And you can see this will do an insert right in the middle, but we're protected from that insert because we didn't see those changes. And you can see that if we run a select again, we will see that new test row is in there. Now, the last one I want to show you here is snapshot isolation. And this is really cool, our optimistic concurrency strategy in SQL that gives us all the benefits that we get with pessimistic concurrency with the added bonus of no locking or blocking. So again, this is really good if your SQL Server can handle it. If you have the resources available, then cool, because this is going to blow up your TempDB database by doing this. All right, so the first thing we need to do is turn it on. You can do that at the database level. You can go to the properties of the database to turn it on, or we can just run an alter database, set allow snapshot isolation on. Now, we're going to do the same thing we just did with serializable. The big difference, though, is it's not going to create a lock or a block while these statements are running. We'll be able to switch over to session 2 and run an insert to get a new row into there, and it'll run it right away. We won't be blocked by the process. But again, we'll still get all the benefits of our serialization isolation level. All right, let's test it out. Let's highlight all this, hit execute. While that's running, let's flip over to session 2, run this, and watch this. See how that was instantaneous? No waiting at all because no blocks or locks took place. And if we flip back, you can see our results are consistent because we don't get any of the side effects that we would get since this is snapshot isolation, which is again much like serializable. So our data was completely protected within our transaction. We got the same results, but in the database it changed. So if we query it again, we will see our test new 2 is in there. In this CBT nugget, we learned about all the things we need to think about when designing concurrent applications. We started off with the basics, where we defined what concurrency is and what a transaction is, and even talked about the optimistic and pessimistic concurrency models. Then we got familiar with the side effects that concurrency brings with it. Lost updates, dirty reads, non-repeatable reads, and even phantom reads. We also talked about all the isolation levels and how we can use them to control our concurrency strategy. From there, we jumped into the virtual nugget lab. We saw how all of the concurrency effects affect our data. And at the end, we saw how all the isolation levels work and how we can use them to control our concurrency strategy. I hope this has been informative for you, and I'd like to thank you for viewing.